let's go for the properties of halogen compounds. One of the important reaction is a nucleophilic substitution reaction. The reaction can be said as a NSR, or technically it is a substitution with nucleophilic, that is SN type of reactions. So this is an allowed terminology or a notation method. Substitution is the main reaction and N will be given. This is further into classified into the substitution nucleophilic bimolecular, substitution nucleophilic unimolecular, substitution nucleophilic I stands for the intramolecular, 2 stands for the bimolecular, substitution nucleophilic bimolecular, 1 stands for the unimolecular, I stands for the intramolecular. So we have a detailed mechanism when we take all these 3 types, we will take later. But let us first let me introduce the core reaction of nucleophilic substitution. The alkyl halides when treated with a sodium salt of a Y minus, the Y minus will attack and X will go out and RY type of product with NaX formation as a byproduct you observe. The favorable condition to take this reaction or to complete the reaction, Y minus is a nucleophile or a base which should be stronger in strength than the so-called X minus. So outgoing group and incoming group strength, if I compare, Y should be the stronger one, then the X will be expelled, and then so it's a nucleophile coming, therefore I call it as a nucleophilic substitution reaction. However, we have a favorable point that when RX bond, if you carefully observe, X is pulling electrons, so therefore X will have a delta minus, R will have a delta positive. That means on the alkyl or on the carbon we have some deficiency of the electron density, so therefore the Y minus is allowed or attracted to attack. How best the Y minus substitute depends on how strong it is. What is the strength here means it is giving electron pair, so electron donors are nothing but the bases, so therefore it can be said as a base. Base means a electron donor. Electron acceptors are Lewis acids, electron donors are bases. So Y minus is donating the pair of electrons. A base definition is that you can observe here like this. A OH minus is giving electron pair and making the water formation. So in this, what is base means electron pair donor. So it is cancelling the acid effect and making neutralization. That's exactly the base here. But what is nucleophile means? A nucleophile will be said when there is a reaction in which the nucleophile is replacing some group and then entering in that place. This is a substitution reaction. When a substitution is involved, the same base I am calling as a nucleophile. In fact, the nucleophile rather is used in the organic chemistry, or in a substitution reaction we are using nucleophile. Base is nothing but electron donor. It's not just donating but replacing also. So therefore, whenever this replacement comes, nucleophile comes. So the order of the nucleophilicity and the basicity also, both are nothing but the giving electron pair, replacing, isn't it? Giving electron pair is nothing but same. So the order of the nucleophilicity and basicity also will be several times, it will be the common. So therefore, it is said that if X is equals to a halogen like a Cl minus, where from the Cl minus is formed means from HCl it forms. So HCl is a strong acid. So therefore, we can conclude that the Cl minus is a conjugate base of this acid, must be the weak acid, weak base. Stronger the acid, weaker the base. It is called a conjugate acid base concept. The HCl is strong means it want to give the proton. Once it is given, it won't take the proton. So that is difficultly it is taking proton, therefore it will become a weak. So that is, in general, it is always understood a pair of conjugate acid and base, if you take, out of them, if one is strong, the other one automatically it will be weak. That is the conceptual point it is. So HCl is strong, therefore Cl is weak. Therefore, in a book it says that if Cl is here, that is a very strong acid base, that is a very weak nucleophile, is that I have a huge number of Y minuses which will replace the X and will get the RY type of the products. First examples let us quote here. What are the different Y minuses available to get the different types of the RY type of the products? Okay. So let us see first examples and then go to the mechanism of the reaction or comparison of the reactions and all that. So while quoting these examples for Y minus, we are interested in the two things. What is that NY I am applying? What is that RY you are getting? That is, RY means product. So which chapter compound is formed? Almost all chapters we are able to prepare, provided I have a chlorine, that is a weak base is there. So many strong bases are going to replace, right? So first of all, the example is with a OH minus. So, okay, so that is a methyl chloride. If I take, add the aqueous solution of NaOH, the OH minus will replace the Cl and you will get methanol product. That is, the chapter is alcohol. So alcohols can be prepared readily by this conceptual reaction. What is this concept here? OH minus, is it a strong one? Yes. The OH minus is a conjugate base of water. Water is a weak acid, so OH minus must be the strong base. So the strong base is replacing the Cl. We are getting readily, the reaction takes place readily. Okay. Even water gives, but sodium salt always ready-made minus will be there. So instead of water, which is the less dissociable one, add water and go on, you have to heat for longer time. Instead, you take a water dissolved NaOH. In the NaOH, ready-made OH minus is there, which will replace, you will get the alcohol. You can take a derivatives of water, that means OR minus, alkoxides if you take. So you can take alkyl halide and a sodium salt of alkoxide. So this alkoxide will replace, and this is already R. Let us take a R and Rx with the OR coming. So you get ROR. This is nothing but ether. This is what a concept developed by a scientist called Williamson. So what is the byproduct? NaCl will come. So the name reaction, it is called a Williamson synthesis. The reaction won a Nobel Prize. In fact, originally the ethers are prepared. So chapter is ether. Ethers are prepared by taking two alcohols. But now in this case, one alcohol converted into alkyl halide, another alcohol is converted into the alkyl, that is sodium salt of alkyl. So Na plus OR minus, the minus group replace the Cl and you will get the ether. So alkoxides are stronger bases than hydroxides even, because the alcohols are much more weaker acids. So alkoxides will be the much more stronger bases than the OH. So readily reaction takes place. Byproducts are salts. So as the byproduct formed more and more, the other product will be the also byproduct and product are together formed. So it is not the side product, it is the byproduct. Make a point. Whenever byproduct stable is the stability is there, automatically that will be formed and our compound is also formed. That is the concept of the Williamson synthesis. Instead of 2 moles of alcohols and removing water, he modified that is Williamson modified into 1 alcohol into sodium, 1 alcohol into alkyl halide. The byproduct instead of water, NaCl will go out. The reaction will become fast. Similarly, NH2 minus, that is a sodium salt of the NH2, NaNH2, when I add, the NH2 minus replace on the alkyl halide and you will get RNH2, that is amines are formed. The reaction when we claimed as a ammonolysis, that is only ammonia also will give the reaction, but let us say sodamide, sodium salt. Similarly, the acids, sodium salt, if I use the esterification takes place on the alkyl halide, use this sodium salt, you will get the ROCOR, that is esters are formed. If alkyl halides are treated with the sodium or potassium salts of cyanides, then cyanide minus will be coming into the compound, that is alkyl cyanides will come. In this case, a slight variation is there. Instead of potassium cyanide, you take the silver cyanide. Rx when treated with the silver cyanide, silver with a C triple bond N will be there. The silver carbon bond has got some covalent nature, therefore breaking and giving minus. Here it's a totally dissociated piece. Minus is there on the carbon, so this is attacking, you are getting a cyanide. Sodium or potassium will give the cyanide. But if silver cyanide is taken, a lone pair on the nitrogen will take this advantages of attacking, because this bond is some covalent nature, it won't readily break up. So this will attack, you will get NC. NC, however, you will have a plus and minus. This is isocyanide is formed. So slight variation in the reagent. Sodium, potassium cyanides will give cyanides only, but silver cyanide will give the isocyanide. Similarly, alkyl halides with either sodium or potassium nitrite, in which the K is plus, O minus and N double bond O will be there. This will be attacking and you will get ONO. This is called alkyl nitrite. Alkyl nitrite is the main product. If the same compound alkyl halide treated with the silver nitrite AgONO, in which once again the CO, that is silver and the oxygen bond is a covalent, so it won't readily break and plus minus. Instead, a lone pair on the nitrogen will attack and you are going to get a RN bond through a double bond O and a coordinate covalent bond. This is called a nitroalkane. Nitroalkane. The reagent is very much similar. Potassium nitrite or sodium nitrite will give the alkyl nitrite, just like cyanide gives cyanide. Silver nitrite is reverse order, nitroalkane is formed. In both the cases, the answer or the pattern of explanation is same. That is because of the covalent nature of this bond, lone pair of the nitrogen is attacking reverse type of the product. However, 100% this won't be formed, that also will be formed as a minor. In this reaction, this will be the minor. In this reaction, that will be the minor. 100% reaction won't be formed. Major product will be the nitroalkane. So minor product will be, that product will be formed here. Okay. So silver is making this type of difference in the product formation. So therefore, you can remember this point. Now the same reaction you can claim alkyl halides when treated with the acetylene sodium salts. Na plus minus. So this minus will attack. Again the same point, that is the acetylene is a very weak acid, it won't react even KOH, such a weak acid. So definitely acetylide anion will be the stronger base which will attack on the alkyl halide, replace, and you will get the R substituted acetylenes, right. So the alkynes are formed. So reagent, remember, and the product forming. Then similarly, the alkyl halides when treated with benzene in presence of aluminum chloride, it opens into minus and this minus will attack on the alkyl halide and you are getting a benzene containing compounds. Alkyl benzenes or arenes are formed. alkyl benzenes can be prepared by this the method alkyl. This is Friedel-Crafts alkylation, but it is a Friedel-Crafts alkylation. It is. The alkyl halides can be treated with the sodium salts of R minus, where R minus will attack and you will get the RR. This is a sodium salts of alkyls are available in the market. You can take RX. The RX in presence of a sodium metal in presence of dry ether, Wood's reaction mechanism shows one Rx converts into R minus and the Na plus. This R minus will attack. It's a Wood's reaction in which RR is formed. This is a Wood's reaction, name reaction. Similarly, when Rx is treated with RMGX, R minus will attack. You will get the RR. This is a Grignard reaction. A Grignard reagent is applying. Instead of this, if you use two, that is alkyls, dialkyl lithium cuprate, R minus will attack and you are going to get RR. In all the compounds you are getting alkanes. Alkane is the main answer, but the reagent is different. Sodium salts of alkyl can be used. In a Wood's reaction ionic mechanism, in a Grignard reaction, this is reagent is called Corey-House. So, we have a Corey-House reaction using reagent RR, in which the odd number of the alkanes, carbons containing alkanes can be prepared. In all the methods, alkanes, that is the attacking species, is R minus. RH, that is alkane, is a weak acid, perhaps the weakest acid, and R minus must be the strongest base, will replace the X minus and you are getting this RR type. Finally, you can also observe a reaction like this. When alkyl chlorides or alkyl bromides, when you treat it with the sodium salt of iodide, I minus will replace, this is a halogen, this is also halogen, you will get the iodine containing compounds can be prepared, alkyl iodides. This is also nucleophilic substitution reaction. You can claim as a L as a reaction. Next one. So, in this reaction, one halogen is replacing the other one. So, this halogen must be the stronger nucleophile than this one. So, therefore, the nucleophilicity order will be the I minus is stronger nucleophile than the Br minus, than the Cl minus, than the F minus. This is understood that the lower halogen is replacing the upper one in a nucleophilic substitution reaction. In oxidizing reactions, fluorine releases the Cl minus, releases the bromide and so on. That is different, that is an oxidation. This is a replacement reaction in which stronger the nucleophile able to replace. This particular reaction is known as Finkelstein reaction. Finkelstein reaction is a name reaction in which one halogen is replacing. Now, what is this order means? This is the nucleophilicity order. Nucleophilicity order. In fact, in general, nucleophilicity and basicity is nothing but same. But in this particular halogen case, the basicity order is different. Basicity order is reverse to this one. F minus is the stronger base than the Cl minus, than the Br minus, than the I minus. How it is possible means we think that the hydroiodic acid is the strongest acid. Hi is the stronger acid. Stronger acid means the I minus must be the weak base. That is what basicity order is like this. How the I minus has become a stronger nucleophile? In general, what we think is a stronger nucleophile, stronger base, like in general we can take R minus, OR minus, and there is something like cyanide minus and a halogen minus. Let us take this is order is common to both nucleophilicity and the basicity order, because nucleophilicity is as a nucleophile replacing the 1. Basicity is 1 gives electron pair, that is nothing but the same. So, in general nucleophilicity, basicity common order, but when comes to the halogens, nucleophilicity order is different, basicity order is reverse to this. So, in the replacement reactions this is allowed. However, while the iodine going out, it uses the its weak base, therefore goes out. So, iodine is a incoming is a stronger nucleophile, while going out it shows the weaker base, therefore it goes out quickly. So, iodination as well as deiodination both are favorable reactions. Iodination is favorable because it is stronger nucleophile. Deiodination is also favorable because it is a weak base, therefore it quit the compound easily, therefore deiodination is more favorable than the debromination or dehalogenation or defluorination. That is what we explain.